rubber starts as latex, which is comparable, I guess, to the good maple syrup from Vermont. As Europeans, we ran into rubber in the Amazon mid-1800s, where the natives were they were coagulating the rubber, and they did that. You need an acid to coagulate, so urine was the chemical, and then they made it into balls and used it to play a game that's like soccer with what would be a softball. That was the source of rubber for probably 50 years. And then I think it was Firestone that started a plantation in Liberia. So the plants, the trees in Africa are a product of the Americans moving and building a plantation in Liberia. Now, the reason for the location is that the trees prosper under just certain conditions, and the ideal plantation is in Southeast Asia, where there is rain every morning and sunshine every afternoon. And so the weather has a impact on how well the trees do. And we will talk a little later in one of the videos that the real risk in rubber is the disease of the trees. And I don't know how many of you know it, but the maple trees in Vermont have a disease, and they're losing trees, been losing trees up there for 25 years. And the same thing can happen in rubber. The other risk is the one that we faced in World War II, and that is that all of the rubber was in Southeast Asia, and the Japanese took that territory specifically for that purpose. Now, in the 1960s, I was in the Philippines, and I was working for B.F. Goodrich. We had a plant on the outskirts of Manila, and I had 3 plantations on Basilan Island. Now, the workforce were locals, they were Moros, and we had a Dutch plantation manager. So to run the plantation, we hired the chief of the local village. So when he came, he provided security. He was the employment manager. Most of the labor, not all, but most of the labor were female. He brought the females with him. They did the tapping of the trees. And we had a few men, and they did the heavy work. Now, this is, you're in the jungle. And so this is local operation, if you will, in the respect of the labor. So I'm sitting on the table on a deck with a plantation manager talking about things we need to do when one of the workers comes running up the driveway yelling something at him that I don't understand. And he said, "Let's go." And we hit it off the porch into the Jeep, down the road. And he's explaining to me on the way that one of the girls has been attacked by one of the boys. And she was, in fact, raped. And before we could get to the trees, they had taken him. They had amputated, castrated him, fed it to him, tied him to a tree, and he had bled to death. So that was tribal justice. And that memory of that particular instance tells me volumes about Americans engaging in foreign policy. Now, the purpose of all this is to get the latex into sheets. And when you see this brief video, one of the things that we'll talk about afterwards is that rubber basically comes from the plantation into the manufacturing sector in sheets, and they are, number one, they are either latex, still liquid, or they come in as number one sheet, number one smoked ribs, number two smoked ribs, or number three smoked ribs. And once upon a time, I was authorized to grade sheets. So let's see this brief video.
Go full screen.
Natural rubber comes from the milky sap of a tropical tree. Thousands of years ago, the native people of Central and South America discovered that the hardened sap was elastic and bounced. They played games with the balls of sap. When European explorers came along, it was soon a whole new ballgame. Today, we make thousands of useful things from the fluid that circulates through rubber trees. Everything from tires to balloons to boots. The seeds are sown on plantations like this one in Thailand. It takes several years for the rubber trees to mature. Then the sap is ready to tap. In the coolness of the morning, when the sap flows freely, the farm worker slashes the bark with a hooked blade. The sap oozes from the abrasion. It spills onto a metal spout inserted below the slashed section. The spout funnels the sap into a ceramic cup below. It flows for about 5 or 6 hours, partially filling the cup. They wait a couple of days for the tree to recover and then tap another section of the tree. After straining impurities, they pour the rubber sap into a plastic tub. They add formic acid and squish it around. The acid causes the sap to coagulate. After 15 to 30 minutes, it thickens to the consistency of tofu. This tofu-like sap has a sticky structure that allows it to now be rolled out like dough. The rolling squeezes out excess water and leaves a ribbed pattern on the sheets that increases the surface area to hasten drying. Then they rinse off the formic acid. They hang the rubber sheets to dry for about 5 hours. As they dry, the rubber thickens and becomes stronger, and the color darkens. The coagulated rubber sap has been transformed. In a few short steps, it's gone from a liquid to a solid. Workers pile the rubber sheets onto pallets and weigh the load. There's a little over 1.5 tons of rubber in this stack. They store the stacks in a warehouse until the next stage of processing. When they're ready to move on, workers peel each sheet from the stack and soak them in water for about 20 minutes. This washes away some of the surface contaminants, but not all. The rubber sheets then go into a machine with many brushes that scrub off more of the dirt. After one more rinse, the rubber sheets are squeaky clean. As you can see, the color of the rubber sheets varies somewhat, depending on the tree they came from, their thickness, and other factors. They hang the sheets on racks to drip dry. They build a fire in a brick oven and smoke the rubber sheets in a chamber overhead for 5 days. It's a slow, low-temperature smoking that preserves the sheets to prevent the growth of mold. After smoking, they clip out contaminants like bark or insects that have become embedded in the rubber. In many cases, they can't get it all. They grade the rubber sheets by examining them against a bright light. Sheets with fewer remaining contaminants receive a higher rating and will command a better price. They stack the sheets according to the grade. And then it's into a hydraulic baler. It presses the stack of rubber sheets into cube form. The dimensions of the cubes conform to international packaging regulations, so they'll fit neatly into containers for shipping. They spray the rubber cubes with a mix of calcium carbonate and solvent. The mixture forms a film on the cubes that prevents mold and keeps them from sticking together during transport. This rubber is now ready for the next factory and the next transformation. It could become almost anything.
George, what's the yield per tree per year?
Oh, I have no idea.
Okay.
I just don't. If I ever
It's
knew it,
10:30.
I've long forgotten.
Looks like they get 60 tappings a year from a tree, and what do they get?
Holy,
A pint a day. So that must.
About 19 pounds.
George,
yeah,
you said earlier that the rubber was found in South America,
right.
and that in World War II, the difficulty was that the rubber came from the Far East. Does that mean that commercial rubber no longer did not come from South America?
No, very limited. There, I don't know the difficulties of bringing the rubber out of the Amazon or why, but we were focused on the plantations in Southeast Asia by that point. And in Africa, you saw some of the difficulties they were having there, which was the social issues going on in the planet. So we had a very large demand, but we had a diminished supply. So we had some rubber coming in, but not nearly enough to take care of all the airplanes and the tanks and the trucks and whatever.
Okay.
So,
George, to what extent do we use artificial rubber from petroleum?
pardon?
I understand that we make artificial rubber from petroleum.
Correct.
To what extent, when we buy a tire or something like that, is it that rubber or from latex or from petroleum?
Okay, I will be getting into this in some more detail, but latex becomes what you consider rubber. Synthetic rubber can come to you almost the same. And most of tires are blends. So in the 1960s, when I was thick in this business, Akron was the home of the rubber industry. And the origin of that is right here in Massachusetts, because Benjamin Goodrich had a plant in the Springfield area of Massachusetts, and he wanted to expand. So he was on his way to Manhattan to try to raise money, capital, to expand his operation in Western Massachusetts. And either coming into Manhattan or leaving Manhattan by train, he happened to sit with several gentlemen who were on their way home to Akron, Ohio. And they were financiers. So they got into a conversation and ended up with an agreement that they would fund Goodrich if he would build the plant in Akron. Now, Akron at that time still is, but is a high point between Lake Erie and the Ohio River. And there's a canal running both ways. So there's transportation from the Great Lakes into Akron and out of Akron down the Ohio into the Mississippi. That happened to be very convenient when I came home from the Orient. I brought a bar with me. This one right here. That Chinese bar from the Orient cost me $27 in freight from Hong Kong delivered to Akron, Ohio. And freight was a factor both ways. Now, at that time, Harvey Firestone, was in Chicago, And he was making buggy wheels, and he wanted to, instead of having a steel rim on the buggy wheels, wanted a rubber on the buggy wheel. And so onto the buggy wheel was a small strip, what, maybe 3 inches wide by an inch thick, just. And so he started buying his rubber from Goodrich in Akron. So now this is shipped from Akron to Chicago. And it had problems. The rubber curing or using it cured or trying to put it on the rim uncured and then curing it in Chicago. So ultimately, Harvey Firestone picked up his business and moved it to Akron, and he built a shed on the back of Goodrich's plant. And in the process of the evolution of this, he developed a wheel that had a ring on the side so he could take the ring off, slide a tire on the wheel, and then put the ring back on. Now, this is a solid tire. There's no air in it. The industry then evolves into having air in the tire, and it has this ring on it so that you can fix a flat tire out in the boondocks somewhere. You don't have to ship your wheel back to Akron or Chicago. And that puts Harvey Firestone in A, the rubber tire business, and B, the rim business. And to this day, that subsidiary of Firestone, I don't know who owns it, but that business is still one of the major rim manufacturers in the industry. And I can talk to you about some of that stuff later. Now, there was a entrepreneur in Akron by the name of Cyberling, and Cyberling opened a business to manufacture tires, but he named the company Goodyear because Goodyear was the chemist that had figured out how to cure or vulcanize rubber. And the process we'll see more of as we go through it, but basically the latex had filler added to it. The major filler is carbon black and other chemicals. Then it gets shaped, and then it is cured at a high temperature and pressure before it actually becomes rubber you can use. Then there was a merchant clothing store, and one of the children of the owner, and that was the general store, one of the children of the owner started General Tire. So we now have 4 companies. Cyberling then loses Goodyear in the market crash of the 1920s. And at age, I think somewhere between 55 and 60, he then starts Cyberling Rubber, which becomes another, they all made tires, but they also made a lot of other products as well, which we'll talk about. Meanwhile, U.S. Rubber is formed by DuPont or with DuPont, but they don't locate in Akron. They locate in Connecticut. But when I was there, we had, I've got here, I think, 4 or 5 major companies. And there were 7 rubber companies headquartered in Akron, Ohio, when I was there. And anywhere you went, it was rubber. And I might add, I don't think I've touched on this, but I will add to you that the Akron, Ohio, as you can see, has the University of Akron has the best polymer chemistry department in the world. And the number 2 is sitting right up the road in Lowell at the University of Massachusetts, Lowell, which I can talk to you about anytime. Let's go next slide. So as this business develops, Firestone and Edison become personal friends. They're both developing, they're both scientific, and Ford. And those families go camping together in the Adirondacks. Goodyear ends up developing a relationship with the Chrysler Corporation. And during the crash from 1929 to 1933, Goodyear delivered tires to Chrysler without getting paid for them for 4 years. Goodyear didn't start getting paid for those tires till after 1933. But when Chrysler put a car on the road, it had Goodyear tires on it. When Ford put a car on the road, it had Firestone tires on it. Meanwhile, U.S. Rubber and General Motors had a relationship with DuPont. And so because of the DuPont relationship, General Motors bought their cars from U.S. Rubber. Next. Next page. Next slide. So this is a burr under my saddle, but everyone is gives a high five to Ronald Reagan, but I have an opposite opinion. Ronald Reagan managed to devalue the dollar, and in the process of devaluing the dollar, the industry changed significantly. B.F. Goodrich ended up being bought by Michelin Firestone ended up being bought by Bridgestone. And this is because their stocks were so cheap because of the devalued dollar. General Tire got bought by Continental. Now, while I was there, in the industry, I was a tech rep. So Michelin was a competing company to us in France. We had our headquarters there. I'll talk about that in a second. Bridgestone, that now owns Firestone, was the ex-Goodyear subsidiary in Japan. And we were busy teaching the Japanese, the French, the Germans, the Dutch, the Swedes, how to make tires. So Bridgestone is ex-Goodyear, and we competed against those in the Philippines. Continental was the ex-BF Goodrich subsidiary. I was the tech rep to there. So that's gone. And Goodyear is the only major U.S. rubber manufacturer left. Next. So there was a little saying in the industry, I had to slip it in here. But at that point in time, not today, but at that point in time when I was there, whatever Goodrich developed it, had the strongest R&D in the industry. Firestone cranked them out. They made them. And Goodyear had the best sales organization. They could sell anything. Now, the automobile that matched that, and the saying went, Chrysler designs it, Ford produces it, and General Motors can sell it. Yet that, during the development of the industry and the vehicle, the auto, and this is heavily the tire portion of this rubber business, Chrysler, they were out there first with various engineering activities, the airflow, the brake systems, front end drive. Ford, famous for his assembly line, and General Motors had their own specialties, but they really were into the marketing and selling of their vehicles. Next. Okay, we're going to take a look at how tires are made. And just a heads up, we're only going to look at the first video.
Today's radial truck tires are masterpieces of applied technology. They have to start, stop, carry, and turn thousands of pounds of truck and cargo at speeds up to 75 miles per hour. And yet we also expect them to last for hundreds of thousands of miles. And we expect to retread them, a form of recycling, to make them last even longer. How can a tire do this? What gives it the extraordinary strength and staying power it needs? To find out, we'll look at what's inside it. Then we'll see what goes into the making of a modern truck tire. We'll start at the outside. The tread, of course, is a thick layer of rubber with a tread pattern molded into it. The rubber is application specific. That means each rubber compound is chosen for a specific combination of qualities, like fuel economy, wet traction, and cut and chip resistance. Treads are often a blend of natural and synthetic rubber because each has unique, desirable performance characteristics. Different additives, polymers, and other components provide strength and resiliency, along with resistance to wear and heat. All are combined, then cured in molds at high temperatures, changing the materials, bonding them together chemically, and forming the tread. The tread pattern is designed to optimize traction and wear. It must grip the road, wet or dry, because the tire controls the traction forces for the truck. But even a tread isn't as simple as it looks. When we cut through it, we see different shades of color in the rubber. Why is that? Well, in most Bridgestone tires, 2 different layers of tread rubber are used. Each has a slightly different color because each has a slightly different composition. The top layer, called the cap, is designed for long, slow, even wear. The layer below, the base, is designed to shield the casing from heat generated as the tire rolls down the road. Heat is the enemy of tire casings, shortening their life. Because retreadability is so important for truck tires, heat must be controlled, and that's why cap and base construction is so important. As we dig further, we find a layer of rubber called the undertread. The undertread provides additional protection for the casing and also helps form the bond between the tread and belts. Different thicknesses of undertread are used, depending on the amount of off-highway service or regrooving required. From this point on, we're looking at what we call the casing. This is the part of the tire that gets retreaded once the original tread is worn away. Below the undertread, we find layers of steel cables and rubber. There are usually 3 or 4 of these belts and a body ply in a Bridgestone truck tire. The job of the belts is to hold the tread flat against the road. Without them, the casing would take on an inner tube-like shape. Footprint pressure would be uneven, and the result would probably be poor traction, poor stability, plus rapid and irregular wear. Steel belts also help tires resist penetration by nails and other road hazards. The cords in each belt run at different angles. That distributes forces evenly and provides great strength. Like the rubber, the steel cord is application specific. Different alloys, different tensile strengths, along with different ways of winding the cords, are used to produce exactly the performance characteristics needed in each part of the tire. Both steel and rubber are specially made to help them bond to each other. Steel is treated with the metal cobalt and brass formulations to help the steel and rubber bond tightly. The rubber that surrounds the steel cords maintains cord spacing and seals out moisture that could cause rust, which could break the bond with the rubber. And steel adds enormous strength. Long ago, a 14-ply rated tire needed 14 cotton layers. Today, just 3 or 4 steel reinforced layers in the belt package, plus 1 layer of body ply cords, do the same job. Beneath the belts, we find another combination of rubber and steel. We notice that these steel cords run at right angles to the tread, and they run radially down the sidewalls of the tire. It is this cord direction that gives the radial tire its name. If you draw a line from the center of the tread to the bead, a radius, you see that these radial lines match the steel cords, hence the name radial tire. As a group, these radial cords are called the body ply and run all the way around the tire. A typical truck tire has approximately 1,200 of these. Each cord runs from bead to bead. As it does, it forms part of the sidewall. The sidewall does most of the flexing as the tire rolls. Sidewalls flex about 500 times per mile and hundreds of millions of times over the tire's life. By flexing and changing shape, the steel, together with the compressed air inside the tire, helps absorb shocks from uneven road surfaces. The sidewalls transmit steering, driving, and braking forces from the wheels to the tread, as well as forces from the road to the suspension system. Although sidewalls don't get the kind of wear treads do, they are exposed to the elements. So sidewall rubber uses special compounds and special additives to protect it from UV light, weather, aging, and curbing. As the body ply cords continue toward the bead of the tire, they suddenly turn completely around the bead and start back up the sidewall. This is called the ply turn-up because the cords actually turn up and head back the opposite direction. Inside the turn-up is a band of many strands of steel wire called the bead bundle. The body ply wraps around it. The space between body ply and bead contains several different kinds of rubber and fillers. Each is formulated to add strength while giving the area stress resistance. The bead is the edge of the tire, you might say, the place where the tire makes contact with the wheel. The bead creates a tight seal between tire and wheel. Since the entire inside of a tire is open, it is the compressed air that forces the beads against the wheel flanges, sealing in the air. There's also a small additional component made of wire or wire and fabric called a chafer. It covers the bead bundle and ply turn-up. It provides protection against damage that might occur when the bead is forced over the edge of the wheel and as the bead moves against the rim flange. Also protecting the bead area from abrasion is a tough rubber compound that helps make beads more rigid for further damage protection. But we have one more component to go. Air molecules are tiny and can literally diffuse through rubber, causing the tire to lose pressure. To slow this, the inside of the tire is covered with what is called an inner liner. This is yet another layer of rubber. Though it's thin, the inner liner actually has 2 or 3 separate layers. One layer prevents air and moisture from passing through. The other helps it bond to the casing ply. 2 more rubber compounds, each with a specific job. Still, even with the best inner liner, a tire can lose 2 psi per month. Another reason to check inflation pressures regularly. We've seen all the major components of a modern radial tire. Now, how is a tire like this actually produced? To find out, we'll visit a Bridgestone Firestone truck tire factory. As we've learned, the basic materials are rubber and steel. About 70% of the rubber in a truck tire is natural rubber, which comes from the sap of rubber trees. About 30% is synthetic, made from petroleum and other materials. Specially made steel wire of a variety of types and thicknesses is used in the belts, body ply, and beads. And there are several specific additives used to help in processing, curing, and strengthening rubber, and in protecting tires against air, sunlight, and ozone. Silica, which is related to common sand, can be added to reduce heat and rolling resistance to improve fuel economy. Different grades of carbon black can also create different performance characteristics. And many secret ingredients can have almost magical effects on how a tire performs. Quality control begins with the incoming materials. Every batch of rubber, every bit of steel, every additive, even the water is tested, first by the supplier to make sure it meets Bridgestone specifications. Then it's tested again by Bridgestone Firestone technicians to verify its quality. And as materials go through the process, they are tested repeatedly to make sure they will perform properly in the finished product. Both chemical and physical properties are checked. We need not only the right materials, but the right strength, flexibility, size, and other characteristics. Nothing can be used to build a tire until it has been tested and approved. Each of the many different rubber compounds is mixed separately. Careful weighing assures precise formulations. At this stage, though, rubber is tough stuff. To mix a batch, you need powerful mixers. These Banbury mixers have 4,000 horsepower motors, enough to power more than 10 semis, and can handle half a ton of rubber at a time. Once rubber leaves the Banbury, it is squeezed between heated rolls called mills. It comes out of the mills in sheets, which may be put back into the Banbury again and again, depending on specifications set by the chemical engineers. And this has to happen for each of the different compounds used to make a tire. Steel is used to make body plies and belts. Multiple strands of wire already wound into cords must be aligned and bonded to rubber. Nearly 1,000 strands pass through guides before being sandwiched with rubber in a machine called a calender. Powerful heated rollers press rubber onto and between the cords. The result is a sheet of steel-reinforced rubber. These sheets are then cut at the precise angles needed to make body plies and belts. Quality control continues in every part of the process. Throughout the plant, giant poster-like charts provide operators with checkpoints for each step in manufacturing. Every critical step is checked and verified before work can proceed. The inner liner, another sheet-like material, is also made using a calender, but it contains no steel. And the other thicker wire will be coated with rubber and wound into sturdy rings that become the beads. Many rubber components are made by extrusion. The largest of these extrusions is the tread, but many smaller ones are used in making parts of sidewalls and fillers. Up to now, we've been making parts that will be assembled to make the actual tire. A person called a tire builder assembles these parts using a tire assembly machine. This is the heart of the tire manufacturing process. Every component is identified and tracked using barcodes. Specifications in computers at each building machine make sure only the right components get used. To make what happens as clear as possible, we'll use animation to simplify and slow down the process. Basically, the parts are laid out on the surface of a big drum. We begin with the wire bands that form the beads. The sidewalls go on next. Then the inner liner is added, followed by the chafers and body ply. With the exception of beads, each of the components has to be matched end for end and spliced together. But it still doesn't look much like a tire. That's where the magic of the tire assembly machine comes in. A bladder inside this new tire is inflated. Then the belts are put into place. And finally, the tread is attached. Bladders on each side inflate, pushing components into the characteristic tire shape. The sidewalls and body ply ends are folded around the beads and pressed firmly against the sides of the tire. A barcode is applied, identifying this tire, the operator who built it, and every component in it, so any irregularity can be tracked back to its source. Special rollers press all the components together, a process called stitching. Because the rubber is still uncured, the various parts are soft and stick together easily. The result is something that looks remarkably like a tire, but it's not cured, so we call it a green tire. We still have to create the tread pattern and sidewall design and vulcanize the components. That's done by giant heated presses that contain the molds. The green tire is placed inside the mold, and pressure is applied from the inside. As the mold closes, the tread segments slide toward the tire, forming the tread pattern and shaping and finishing the outside. Inside the air cavity of the tire, a rubber bladder, sort of like a big inner tube, inflates to press the inside of the tire against the mold. Molds are incredibly precise and very expensive, $50,000 to $70,000, as much as a small house. And you need separate molds for every tire size and every tread pattern. For popular tire designs, you might need dozens, even hundreds of molds. Green tires are heated at precisely programmed temperatures and pressures for precisely controlled time periods. High-pressure steam provides the heat and sometimes is also used to generate electricity, reducing both power bills and pollution. The process is called curing or vulcanization. It bonds the components of the tire together, forming chemical links between rubber molecules. Curing changes rubber from something sticky and soft in summer and stiff and hard in winter into a tough material that provides remarkably predictable performance year-round. Once the tire is cured, you might think it's ready to use, but there are a few more things to be done. Quality control, which has been continuous throughout manufacturing, now looks at the finished product. X-ray machines see steel cords inside the rubber to make sure they are properly aligned and properly spaced. Any tire that doesn't meet specifications is scrapped and may be recycled as clean-burning fuel, or may be made into flooring or even asphalt. In addition, each tire is checked for balance. This machine marks the light static balance point of each tire with a yellow dot. This makes achieving initial static balance easier when you mount a new tire. Again, if the tire is outside specifications, it is scrapped. Some tires are also marked with a radial force variation mark. Like the static balance mark, this helps reduce ride disturbance by helping you mount the tire for minimum vibration. And skilled operators examine each tire by sight and touch for quality. They give each tire the final okay to go to you. Tread patterns and sizes are sorted, labels are applied, and the tires are sent to warehouse areas for shipment. At this plant, a robotic warehouse system stacks, stores, and retrieves finished tires to fill orders without requiring any human labor. And quality control still hasn't ended. Bridgestone Firestone technicians routinely pull random samples for testing. Tires are tortured on test drums, punctured by hydraulic rams, cut up and examined with microscopic precision. Technicians compare final products to specifications, looking for variations that could diminish performance, tread life, or retreadability. It can take weeks to test a tire, but it's an important job because it assures consistent quality. And tires aren't tested only in the laboratory. At the Bridgestone Firestone Texas Proving Ground, tires are tested a variety of ways, including running on a 7 3/4 mile oval track, and put through tests designed to simulate the kind of abuse real tires get in the real world. If the tire is a new design, it will also be given extensive field trials before being released to customers. Only when a Bridgestone or Firestone tire passes all these tests is it ready for you. And even then, field engineers and sales representatives monitor the performance of tires on customer vehicles, paying special attention to anything out of the ordinary. The results are some of the finest truck tires available for virtually every application and every vocation. Truck tires with incredibly long life, extraordinary traction and handling, and that provide low cost per mile by maximizing retreadability. With good maintenance and careful retreading, some of these tire casings have provided their owners with over 1 million miles of service. So why do Bridgestone Firestone truck tires deliver such outstanding performance? As we've seen, it's the way they're made, the advanced methods and materials they're made of, and the people who make them.
So what we're going to do is we're going to finish off on tires and questions, and then we'll do the industrial products a different time. So prior to making tires the way you've seen it, the sidewalls of tires were not made radially. They were made at a 45-degree angle or close to a 45-degree angle. So the fabric was crosshatched, and you would have a 4-ply tire that would be 2 plies going one direction and 2 plies going the other direction on the sidewalls. And then radial tires were born in Europe after the war. But there were no rubber plants after the war. We bombed them out of existence. So they were all new plants. So they were making, like many other products, steel in particular, they were making tires with a different pattern. This was this radial pattern in Europe. And the United States had all of this billions of dollars of investment in their processing equipment, as you can see, and they were in no rush to change it to a different pattern or design. So one of the tasks that I had was our subsidiary, the Goodrich subsidiary in France, was Kleber-Cologne. And Kleber-Cologne was competing with Michelin, and they were both making radial tires. And so I had the pleasure of bringing the technology from France to Goodrich in the 1960-ish. But in order to change it, we had to close an entire place, like closing a truck, automobile plant. Had to close the plant and mostly bring in new machines. In some cases, it was altering existing machines, but it's new tooling, it's new dies, and to some degree, it's new machinery, big capital equipment. The vice president manufacturer of the company brought my partner in and said, I want to. He said, we've studied this and economically it doesn't make sense. He said, and then I put another team together and they studied it and said it doesn't make sense. So I put a third committee together and they've studied it and said it doesn't make sense. And then he looked at the 3 or 4 of us. He said, God damn it, I want a report that says we have to do it. now go study it. So that's what it took to get radial tires. And with radial tires, the mileage on your vehicle is about 50% more than it was with the old bias cut tires. Okay, that's the end of that.
At the time that tires changed from, I forget what the old word was, bias ply, I forget what the name was.
Bias cut.
Right, to radial, the cost of tires must have increased as well, correct?
No. The tire. Let's see. I don't know that I have a cost comparison for you. The tire in those days our cost to the original equipment was $8. The cost to you was probably $20. But the cost did not change. The material was almost identical in cost. The manufacturing cost, I don't think it was that much different.
Actually, George, I remember a period where the cost of tires went down quite a bit. When I was a kid, people would routinely ride around on bald tires because they were so expensive. And then a while later, a number of years, people rarely did because the cost of the tire went down quite significantly, as I recollect. Do you remember that? This would have been from the 50s to 60s to 70s.
No, I don't.
George, what makes the radial tire a better tire than the old conventional one?
The biggest part of that is that, and I can get into this either later this morning, but the enemy of a tire is heat. So when you are whizzing down the highway and you have 4 plies or 6 plies, or on a truck tire 12 plies of sidewall, as that tire turns, the sidewall is flexing. As it flexes, it is generating heat. So the more plies you have, the more heat you are generating. And with a radial tie plier, they were able to have fewer plies in the sidewall. And then therefore they generated less heat. And because they generated less heat, they could have a lighter tire, rely more on the fabric than the rubber, and get longer wear and a lower cost.
I know that in the 60s and 70s and maybe even 80s, I probably got a flat tire at least once a year, and I probably had a blowout maybe 1 year out of 5. And they were damn dangerous. In the last 15 or 20 years, I think I only had 1 flat tire when I ran over a huge nail. And I don't think I've had a blowout since, I don't know, maybe the 80s.
Maybe your driving has improved, John.
I've had similar experience.
You don't see cars by the side of the road getting jacked up either.
No, you don't. So it's obviously not just my extremely capable driving.
Isn't it the sidewall is stronger now and it doesn't bubble out like they used to?
Yeah, that's what George said.
Yeah.
That's what George said.
And you've got, remember now that in the 50s, you had a tube in your tire. And we went from a tire with a tube to a tubeless tire. And that was painful to some degree in terms of making sure that your tire doesn't leak. That means your rim has to be perfect as well as your tire.
I think also the elimination of glass bottles. I mean, it used to be that all the Coke and Pepsi bottles were all glass and people would throw them out of their car windows and there'd be a ton of glass on the highways. Now that's all basically gone. And the worst thing you'll run over is a plastic bottle.
Now the local streets have a tendency to have more building materials that get dropped onto them, like roofing nails. That's where I run into my problems.
But I think, I suspect, I have no data, that a lot of the flat tires were due to all these bottles.
Yeah.
Now we make a lot of plastic and put them in the ocean.
Right.
Yeah.
Well, you can still hit a curb. You can still hit a curb hard enough with a sidewall to blow your tire. I can tell you that from personal experience.
I did that a year ago.
Yeah.
Yeah, and bad mounting also.
Or a pothole.
As rims age, you start getting rim leaks.
Now
the other thing is the rims are getting really expensive.
George?
Yeah.
I remember
when the industry was trying to transition from the bias tires to the radial tires, there was some resistance in the US at least, because the bias tires always looked underinflated compared to the radial tires looked underinflated compared to the bias tires. You remember anything about that?
Yeah, the sidewall shape. Everybody said I have the tire's underinflated because it flexed.
Right, exactly, yeah.
I still have that problem. You know, I can't look at a tire and know what its inflation might be, whereas I used to be able to tell.
Yeah.
Well, if the rim is on the ground, it's a short tip off.
I used to know what things cost, and I don't anymore.
Well,
with tires, with the bias tires, they actually had to start introducing sensors that tell you in the dashboard when you're underinflated, because you can't just look at it.
well, there have been changes. The principles haven't changed so much, but there's all kinds of refinements. I mean, to have a sensor on your dashboard that tells you whether your tire is underinflated or not, you know, that's not the sort of thing you had.
Well, now the problem turns out to be, how do you get to turn that light off?
Fix your tire.
Exactly.
Well, after they put it, you change your tires. You know, I bought a car, it had a new set of tires on it. It took me a month and a half to figure out how to turn off the damn light.
They have to recalibrate those. And if you go to a place that specializes in tires, they automatically do that. There's a place in Watertown I go to, and they do that.
Yeah.
But they also discovered I had 3 bad sensors.
Okay, there you go. Or you spend several weeks looking on the internet until you find somebody who gives you the magic recipe for recalibrating your own car.
Yeah, if you have to do it yourself, there's a recipe.
It happens every winter to me when it gets real cold, then the tire rotation varies between wheels, and then it never unlatches unless I software program it back.
Well, some cars have a switch. I know my car has a switch for 2 sets of tires, so that if in fact you might change tires to winter tires, you can flip the switch and it says, oh, this is the winter tire setting. Everything's cool. And then when you put them back, it's the summer tire setting. So it remembers 2 different settings so that they're not, you know, the computer doesn't think one is over or under inflated.
George, I have a question. You talked about plastics and the problem we have with plastics about 2 weeks ago. What happens with tires when they wear out? How are they recycled? What happens to the components of the the rubber aspects of the tires?
Okay. I have a segment on that, and I will include that with industrial products.
First of all, let me just thank George for doing, as usual, an absolutely wonderful job.